Hello and welcome to this episode of Physical Attraction. In this episode we'll be finishing up our review of direct air capture and then negative emissions technologies as the full series in general. We'll try and go over some of the things that we've learned about these negative emissions technologies, some of the general principles that I think you can take away from learning about them, and overall an assessment of what we've covered in this series. But first up, to finish the review of direct air capture, it's probably worth discussing some of the individuals and companies that are trying to do this now in a little more detail. In part, it's really seeing how this often gets covered, particularly in popular science literature, which made me want to cover it on the podcast in such excruciating detail. Over the last few years, you must have seen dozens of articles with headlines like, "This tiny startup is developing technology to suck CO2 out of thin air." And the responses that you get to these articles, which generally speaking almost write this up as if it's a brand new technology, are always a mix of, "Yay, we found the silver technological bullet to solve climate change," or alternatively, "This won't work and we should plant trees instead." If nothing else with this series, what I hope I've been able to do is give people enough information to form their own opinions, even if you disagree with me about how genuinely useful negative emissions will be, or which technologies have pros which outweigh their cons. So going on to the people who are doing direct air capture now, Climeworks is one such company. Based in Switzerland, they were founded in 2009, and since 2017 their device has been capturing around 900 tonnes of CO2 per year. The CO2 is then mostly sold to a nearby greenhouse operator for use in fertilising that greenhouse, which helps to partially offset the cost of the capture, but the business still relies on government and private funding to keep afloat. To say this is a small enterprise is an understatement at the moment. Indeed, just for fun I worked out that assuming that they all have average carbon footprints for Switzerland, the 114 employees of Climeworks are probably responsible for around 500 tonnes of CO2 themselves a year, with 900 then captured by the operations. Even then, with the CO2 being used in greenhouses, it's not clear to me how much of a negative emissions process this is net. I mean, what happens to the CO2 after it's fertilised the plants? Presumably some is allowed to escape, but it's not clear to me what happens there. So really, this is at best a proof of concept, and of course that's all it's really intended to be. Now, at present, their cost of direct air capture is around $600 per tonne of CO2. So when we talked about that House et al. Paper in the last episode, which estimated $1,000 a tonne would be the cheapest you could get it, obviously that's already been exceeded by people in practice, and this is a prototype. So I think it's not unreasonable to suggest that you could get down to $200, $100 a tonne. Their present goal is to get it down to $200 to $300 per tonne by 2024, and Carbon Engineering, another firm that's run by David Keith, their long-term goal is also $100 per tonne. But I think it is worth picking on Climeworks a little, just because once you get these little businesses set up, it sort of illustrates how hard the road for direct air capture may still be. It's true that they can offset around half the cost of their CO2 capture by selling it to this greenhouse. But the only reason they can do that is because they're far away from other sources of CO2 in Switzerland. If they were close to other operations that were producing CO2, the price of CO2 would be less and they wouldn't be making as much money from it. And of course they can also only do that because they're producing it in fairly tiny quantities such that they can sell half of it to this greenhouse. Otherwise, there's not going to be a demand for it. And these dynamics are just not going to prevail if CCUS takes off in a very big way. In this imagined future, we have billions of tonnes of supply all over the world of carbon dioxide. So much of the stuff we don't know what to do with it. And so this idea that you could make a living selling 400 tonnes of it to a greenhouse or even offset your costs in that way is clearly not going to scale up unless we find some pretty major uses for CO2. There's a very, very limited amount that can practically be used by greenhouses. And if CCUS did take off in the way it would have to, the price of CO2 would obviously plummet and the business would then become much less viable. So even the fact that Climeworks has been able to do this, and of course has required, as we've mentioned, private capital and government grants, it doesn't necessarily demonstrate that they could continue to do it once they've scaled up. It's the problem that you have of being a victim of your own success in some of these industries where as you continue to produce, the price of what you're producing goes down, and therefore, unless there's a increasing demand for it as well, you may end up not having the margins that you did at the start of the business. As we've discussed on the episode about utilising CO2, its lack of practical applications at the moment, save for, ironically, enhanced oil recovery, means that it's difficult to see how anyone is really going to make money doing this. Now, I should say, obviously, there is no logical inbuilt requirement to the universe that says you can run every kind of service or perform every kind of task in a way that makes a profit. Some things you do for other reasons, It's just that increasingly this is the logic on which we run our societies, and it's a logic that's built into a lot of ideas about what feasibility is. And so it's not feasible to do this unless the cost can be offset somehow, in the eyes of many people who are studying this stuff or considering it. But it's just worth remembering that when we talk about profitability and how it gets paid for, there is no law that says cleaning up your own damn mess is going to make you a huge stack of profits. And while the advocates of carbon utilisation suggest that we might have even a market for perhaps a gigaton of CO2 a year by 2050, that's obviously not going to happen by itself. That will require a lot of support to establish that market and to get the technologies going that will make people use that market. And even then, that's still only 3 to 4% of our emissions each year at the moment. And there's no guarantee that the price that would be set on that market for a gigaton of CO2 would be enough to pay for the expense of pulling the CO2 out of thin air. Indeed, pulling it out of thin air is going to be a much more expensive way of producing CO2, if there genuinely was driven by the demand for CO2, than pulling it out of exhaust fumes from fossil fuel power plants and so on, and other ways of producing it, including, I guess, burning stuff that has carbon in it, which would be a bit counterproductive, wouldn't it? So you can sort of see the point that just because, even if you can imagine all of this CO2 coming to use and not just being buried, it's very difficult to see how, even with that utilisation market in place, that's necessarily going to mean direct air capture is going to be the thing that we do it for. But take that notional profit out of the picture, and someone somewhere is going to have to eat a big cost to make direct air capture viable. We know that technological development is not just a matter of first-order innovation or blue skies research that leads to these step changes in efficiency. You do need that deployment, like we talked about with solar panels in the episodes on discourses of delay. Advocates for extremely technological solutions like direct air capture will point to how costs of things have come down rapidly with Moore's law and computing and with solar panels and the price of those things. But the difference is that those items had stepping stone applications that would motivate you to take up that initial cost. A very big and bulky computer is still useful to some people, and useful enough that people would want to develop them for research purposes, for military and industrial purposes, before eventually we got to the stage where it was cheap enough for home computers to be viable. Similarly, with solar panels, there were initial applications in terms of satellites and space where they had a clear advantage over many of the competitors, and that was part of what motivated people to develop them. Again, for remote outposts and so on where you needed electricity, it's another great example of where that can compete with a fueled source of power. And those stepping stone applications were what allowed that initial build-up of the capacity to take place. But with direct air capture, it's really not clear that there are going to be these stepping stone applications which you're going to need to do it for, and therefore this idea of how it's going to bridge the valley of death towards becoming a very widely used technology is still extremely difficult to see, I think. That huge initial cost to bury the first, say, billion tonnes of CO2 using direct air capture, which will be the most expensive tonnes to bury, someone is going to have to take that on. And I think without that, the industry is going to struggle to develop in any meaningful way. Like all negative emissions technologies, I think it exists in the shadow of what isn't there. I think we've stressed endlessly in this series how negative emissions technologies can fit into decarbonisation, but the most viable and obvious way for them to do that is as quite a small component that cancels out very hard to mitigate sectors for carbon dioxide emissions, and not something that scales up to cancel out all of our emissions so that we can continue doing business as usual. But in order for them to even scale up to the point where they can do 5 or 10% of our emissions and cancel out hard to cancel out emissions from aviation or industrial processes or whatever, then you still need mechanisms in place. And I think that the negative emissions technologies exist in the shadow of what isn't there. The mechanisms that would force polluting industries to pay for cleaning up their waste, or the big, globally applied carbon taxes that would make it financially worthwhile to actually bury a ton of CO2 and get some sort of credit for it. You know, whether it's a market-based mechanism, whether it's a global regulation that forces you to bury your CO2, whether it is mechanisms that force industries to pay for the waste, or whether it's mechanisms that add to the price of carbon-intensive activities, any of these things could be a way of getting it to happen, but by and large they don't exist yet. And even in places where carbon trading mechanisms do exist, like the EU's emission trading scheme, the price of these credits is not high enough yet for people to actually be motivated to run direct air capture as a business whose sole purpose is to clean up CO2. So I think it's fair to say that, if negative emissions are going to arise at all, then they will be a solution for that last 5 to 10% of hard to mitigate emissions. But the only problem is that if we want that technology to be available even at that scale, on the timescales we might need it by, we need that incentive structure in place to kind of start being there now. And that's not currently happening. What's more, the fact that direct air capture is initially seen as, and actually is, more expensive than the competitors, give it a serious problem in getting that foothold compared to other technologies. Let's assume that negative emissions isn't just going to be lip service or an excuse for inaction, and the programs that we've already seen recently start to scale up, and soon there's a market for millions of tons of CO2 removal per year. Perhaps, in the example I'm talking about, this would be for companies that want to obey green regulations, tout their green credentials, individuals who want to cancel out their carbon footprint, and they're paying someone to bury the CO2 for them. And I think it is viable that market could get up to millions of tons a year. I think that is viable even perhaps on a voluntary basis without a major regulation, because we have seen big tech companies, for example, starting pledges that are going to say, okay, we're going to cancel out even our historical CO2 emissions. And if you're doing that, then the simplicity of being able to pay a direct air capture company and not have to change your operations that much might end up being appealing to people, even if it is slightly more expensive. But then, of course, you are competing with other negative emissions technologies to deliver that same service and to satisfy that same market. And then it comes down to how these projects are actually financed in practice. In this, I'm going to hark back to our series on nuclear fusion. We talked about Maury Markowitz's cynicism when it comes to actually getting nuclear fusion power plants funded, even if the technology is successfully developed. Because the trouble is that the incentives that technology advocates might have aren't really necessarily on the minds of people who can actually fund it. You'll remember that we talked about how in the nuclear fusion case, you can be a big fan of the technology, you can think it's really cool, you can talk about the advantages for nuclear proliferation, you can talk about the baseload power that it might be able to supply, you can talk about the potential for it to be a limitless power source long into the future, etc., etc. You can talk about the reduced risk of meltdowns compared to fission, whatever it may be. And the thing is, all of these things will be of secondary concern to the people who you'll generally be relying on to finance your project. Because the first and primary thing that the people who are financing your project will be concerned about is, how much money do I have to put up now? And what percentage return will I get on it? And you can have a technology that's as good as you like, or has all of the advantages that you might like from a sort of scientific or societal point of view. But if your answer is, you're going to have to pay me more money and get a slower return than in the case of this other project, like a more modular renewables project where you can just push up wind turbines and solar panels very quickly, then that's going to be very difficult to persuade investors to get on board. We saw in the nuclear fusion episodes that this is in part why fission has been so difficult to build without government support, and the fact that these are big capital-intensive projects means that cost overruns and delays have become associated with nuclear fission projects in the West. So, in some ways, it's this practicality that is actually the predominant one when it comes to people allocating money and allocating resources and making decisions about which technologies to build. And all of the arguments about nuclear versus renewables that nuclear advocates will have to acknowledge that if they're going to get anywhere. Well, you could say something similar about direct air capture, right? I could be a huge advocate of direct air capture and wax lyrical to you about the advantages. It takes up less land, it doesn't compete for agricultural or ecosystem space, the carbon accountancy is more reliable, if you invest in it, the cost will go down over time and compete with other sources and so on. Maybe all of that is true, but if the person buying the carbon credit and financing the project, they're probably not going to care. If someone tells them they can remove a ton of CO2 by planting a forest or doing some BECCS somewhere, and the credits are all the same and fungible and interchangeable, but the afforestation credit is half the price, they're obviously going to go with that as the solution first, even if the net effects of everyone doing that might end up being worse for the environment than the optimal mix of technologies we can dream of in our models or fantasies about the future. And this isn't really a profound statement about which technology is better, it's just about the sort of evolutions you can expect to happen under market-driven mechanisms. So overall then, what can we really say about direct air capture as a negative emissions technology? In some ways, it's one of the most intriguing and frustrating of these technologies to cover. As with many of the others that we've covered, we know that it works in principle, but scaling it up in practice is much more difficult. Some people imagine that a machine that sucks CO2 out of the atmosphere really will solve all of our climate issues, generally if they're not thinking about the scale of the problem. Others almost instantly and instinctively dismiss the whole process as too expensive and too inefficient to possibly take place. Why build a complicated machine when we have trees that will do a similar job? Why rely on humanity's willingness to pull CO2 from the atmosphere at tiny concentrations, having failed to pull it from power plants at much higher concentrations? Aren't you just falling into the same trap of hoping that massive industrial processes, economic and technological progress and growth will solve the problems that they have created? Isn't it just allowing the ultimate techno-fantasy to provide further excuses for delaying urgent action to cut emissions? I can see people viewing this as a sort of band-aid that we would put on our problems when the problem might be more fundamental. And maybe you're hearing these questions and they might be resonating with the thoughts that you've had listening to this episode. So on one of that first and most obvious questions then, why we would choose to suck CO2 back out of the atmosphere at a concentration of 450 ppm, when we can't be bothered to capture and store it from the exhaust of fossil fuel power plants and industrial plants with conventional CCS. Obviously one of those tasks is physically much easier. The approach of doing direct air capture where CCS hasn't taken off is maybe a bit akin to starting a blood transfusion before applying a tourniquet. Now, I obviously agree with the analysts who point out that because direct air capture at scale requires you to already have the infrastructure to transport and bury CO2 at scale, it would be a bit bizarre for direct air capture to exist at a massive scale without CCS from power and industry. This is also true of BECCS, by the way. You would expect, if you're using bioenergy and carbon capture storage for negative emissions, then why would you not also have large amounts of carbon capture storage on your positive emissions as well? And then we need to go back to the problems and concerns, pros and cons raised with those ideas as well. But there are some valid reasons why I think this is the case and why people are talking about direct air capture. There was an interesting discussion on Climate Twitter recently from Shail Khan asking why so many startups are focusing on direct air capture and not CCS, given that the latter is the easier, technically, and arguably more urgent problem. And I think the answers in that thread, including from Tim Latimer, actually go some way to explaining why we're transfixed with direct air capture and negative emissions more generally, while we haven't entirely implemented the solutions we know we'll have to implement anyway, whether that's CCS or reducing emissions through some other way. Part of it is this classic thing of techno-optimism, the belief that we're a technological breakthrough or two away from solving climate change. I don't really need to talk about that too much by now. It should be clear that having these cheap technologies available is helpful, but it's only part of the story. But maybe if you haven't spent years obsessing over this like many in the climate field have, direct air capture is a simple story to tell that can feel like a magic bullet. It's easy to explain. Technology chucked CO2 into the atmosphere, so we'll invent something that will pull it back out again. In addition, for the sake of why there are so many startups focusing on this, part of it is because it's easier to pitch to venture capitalists, because it can seem more sustainable. Compare it to CCS. If you're talking about vanilla carbon capture and storage, you're retrofitting fossil fuel power plants, right? And effectively what you're doing there is allowing fossil fuels to reduce the damage that they cause, which sort of continues our dependence on them. So it can be seen as a less sexy industry waste management type solution. It has fewer obvious customers that you can talk about as well. In a world of carbon taxes and markets, direct air capture is sort of letting you print carbon credits at a profit. And that might potentially bring you a lot of different markets for people who would be interested in offsetting their CO2 emissions by burying them. But in the case of CCS, you obviously have to work with the fossil fuel companies or the industry that is currently emitting that CO2, if you want to fit that to a plant. As well as that, direct air capture can pose as reversing climate change. And that's a much grander and sexier mission statement, even if you might clearly see that it would need to be scaled up to a much larger extent to do that. You can talk about it having more customers and more industries who might want to use it. And I think those are big reasons why it's being seen as, in some ways, a more interesting business proposition for these startups than ordinary CCS. The other thing, of course, is that direct air capture projects can be modular. In the case of Klaus Lackner's trees or Climeworks, you can build prototypes that are sucking in a ton a day or so, more or relatively quickly and easily. And that gives you something to show for what you're doing. It gives you some progress, some sort of modular progress and some concrete results on the investment. And it does also increase the range of potential buyers you might have. Klaus Lackner talked about manufacturing his trees in a sort of similar way to the car industry does, but in reverse. They would be inverse cars, sucking in CO2 rather than putting it out again. And, I do think that if you're manufacturing this in a modular way, it does increase the range of potential buyers you might have. And I think that's probably one of the best arguments in direct air capture's locker. You might have an initial market for businesses or individuals who want to cancel out their carbon footprint through burying it. And you can sell them the credits. It gives you this initial marketplace. Of course, one of the issues with this is that this presupposes that the carbon credit and offset market can actually distinguish between something like direct air capture, which I would argue is pretty direct in terms of how directly you buried the CO2, and some more sketchy, well, I paid someone not to burn down a forest, which counts as an offset of a ton of CO2 somehow type scheme, which is another thing that you'll see. But in the case of CCS, carbon capture and storage on a fossil fuel power plant, you don't have as many potential customers because you're immediately talking about a very large-scale building project that will probably cost tens of millions, that will require a lot of initial capital, and you need to partner with someone who is running the existing fossil fuel power plant to do it. And of course, when it comes to why startups are interested, there's also the novelty factor. We've talked about CCS now for decades. It was a saviour technology in the 90s and noughties. You can go back and find all of this great literature from the industry and from people discussing these techs and saying how they're going to come along and help us. The fact that it didn't really take off so far hasn't dissuaded our optimism that new technologies might succeed where it seems to have failed. And CCS doesn't have the novelty because we know what these projects look like in practice. They're these big engineering projects with a big initial capital cost that we're increasingly bad at doing. The fossil fuel industry, the fossil fuel companies, energy companies, they don't want to pay for it if they can possibly avoid it, because it eats into their profit margins of their primary business, which is burning fossil fuels. Hence, many of the pilot projects almost seem to be done to show that it's possible, and you could even argue to give the industry a veneer of credibility when they argue that they might be carbon neutral someday. If the fossil fuel companies are in a mode of not really taking this seriously, then it's hard to market to them, and until they're spending substantial fractions of their capital expenditure and research and development budgets on CCS, until they're actually putting rules in place saying, by 2025 or 2030 or whatever, we're going to have all of our industry is going to be retrofitted with CCS, it's sort of hard to believe that this is being taken seriously. And then if you're marketing it to them, then it's hard to market to them if they're not really taking it seriously. Direct air capture is easier to market and imagine. And I think this gridlock, this deadlock, is part of the reason why some scholars have suggested that the CCS industry is in need of something major, like laws which would make it mandatory to sequester a certain fraction of your CO2 emissions, or, on the market-driven side, a very high carbon price to actually take off. Of course, when it comes to CCS projects, governments don't really want to pay for it if they can possibly avoid it. And if they're climate conscious, I think a lot of them will recognise that there are cheaper ways to reduce emissions, such as switching to gas or renewables or shutting down the fossil fuel power plants altogether. And investors don't want to pay for it because with high initial capital costs, relatively untested technology, just as nuclear fusion is, it's the kind of project that investors are generally quite shy of. Before we get into the fact that without a robust carbon price or someone willing to pay you to bury the CO2, it's just costly waste disposal. This is the whole point in a sort of macroeconomic point of view after all, right? Is that we're effectively paying fossil fuel companies a subsidy by allowing them to dump waste on a massive scale. And that will generally be less expensive for them than actually having to do something with the CO2 and bury that waste, unless you have this carbon market in place. And so we come back to this point of that I talked about in our first episodes on negative emissions, where I said you can see business proposals that have been done by consultants and so on for negative emissions companies that look great and seem to work, except they don't know how they're going to make any money. And it comes back to the question of really what is the best mechanism if we as a society decide that we want to get this done. Combine these factors though and you can see why direct air capture is getting more attention and at least venture capital investment than CCS, which I think has started to accrue a bad reputation for cost overruns even when its projects do succeed. Now I hate to be the guy who always sits on the fence so long that the iron has penetrated into his soul, some people might say, but I do still find it quite difficult to come down on either side a hard judgment call to make. I think it's too easy to either fall into the trap of painting this as a saviour technology, or else just dismiss it out of hand as techno-utopianism that will never take off. And I don't really know. I can easily imagine a world where in 20 to 30 years direct air capture is like CCS today. There were a handful of pilot projects, some of them were fairly big, but they never really got beyond 0.1% of emissions or so, because no one has really forced the issue to that scale that makes a really big difference. And if they never really advance beyond that scale of proof of concept or second or third of a kind and bridge that terrifying valley of death that all technologies must bridge if they want to be adopted into the mainstream, I could see that happening. I could see that being the case in 2040 and 2050 when we do the 30th anniversary editions of this show and reflect on all the stuff I got wrong. I can imagine that. But I can also just about imagine the direct air capture utopia where these machines are quietly sequestering some impressive volumes of CO2. Even the advocates admit that this is hard. In the New York Times, Stephen Pasala of Princeton, who is an advocate, said, "The idea of bringing direct air capture up to 10 billion tonnes by the middle or later part of this century is such a Herculean task, it would require an industrial scale-up the likes of which the world has never seen." So that's what he says, Stephen Pasala of Princeton, even as some of our models are starting to say that we might be bringing direct air capture up to 10 billion tonnes by the later part of this century. Glenn Peters, the climate stats analyst and scientist we've quoted several times on this show, points out that operating a facility like Climeworks' proposed 1 million tonne per year facility requires a small power plant at least to operate it. If you want to scale that up to, say, 10 gigatons per year, a quarter of emissions today, then by mid-century you need 10,000 such facilities. One a day for the next 30 years would need to be constructed. And all of that power has to be clean, and this effort has to come alongside all of the other things that you need to do to follow that decarbonisation pathway with a large amount of direct air capture. So again, you need to be building 10,000 small power plants, one a day for the next 30 years. And one thing that people will start to question and point out is, if you can build power plants at that speed and at that rate, then would it not also be possible to consider building them to replace fossil fuel generation altogether, rather than having 10 gigatons of DAC? And is it that much easier or more difficult a task than other alternatives, such as reducing our demand, such as radical energy efficiency policies, such as huge rollouts of electrification and renewables? This is the problem we're talking about here, is that however we solve this problem, if we're trying to do it in 30, 40 years, the effort is going to be Herculean. And this Herculean effort to get 10 gigatons per year, or a quarter of our current day emissions, is it more or less Herculean than other efforts? It's difficult to say, isn't it? None of what we're going to be able to do is going to be easy. And so being able to envision it hardly makes it likely. But then you can ask other questions. Is it really that much more ridiculous to imagine than the BECCS and afforestation utopia, which many models are so keen to project for the future? The IPCC, most of its models have had BECCS in them. We've talked about tens of gigatons of BECCS, 5, 6, 7 gigatons. Very common in the models that keep us to below 2 degrees Celsius. Our mainstream climate accords increasingly rely on that modelling and that projection of the future. That vision of the future is something that is considered to be a mainstream thing with BECCS, and yet is it actually that much less feasible than direct air capture? Is it that much more feasible than direct air capture? I think that the BECCS and afforestation utopia models massively underestimate how difficult it is to just change the land use across huge swaths of the world territory. The advantages of direct air capture then are clear. It can seemingly scale more easily and without the limitations that apply to some other technologies. And depending on how much you're willing to pay for it, the carbon accountancy is more straightforward, less liable to have unforeseen consequences or adverse effects by messing around with natural systems to enhance those natural sinks. It's a chemical cleanup operation ultimately, and the fact it has to occur at a vast scale because our chemical problem is so huge doesn't make that any less true. The main prohibition is still the cost. Unfortunately, even as the technology develops, that may still prove to be its downfall. After all, in a world where we can't decarbonise fast enough, and avoiding a turn is generally much cheaper than removing it later, how viable is any scenario where we have huge amounts of negative emissions? These things show up in these models where we sort of force the model to solve for a certain temperature, but there's no guarantee that the world is going to be forced to solve for a certain temperature in the same way. If people look at these models and take them seriously as projections into the future, then some of them are saying that there'll be a market for 10 billion tonnes of CO2 removal a year by 2050. You would think that someone would be pretty interested in desperately working on technologies now that would capture that 500 billion a year industry some years down the road. There are a few signs of this starting to happen, and clearly if you were pitching a direct air capture company to venture capital, that would be your first comment, right? This is going to be a 500 billion a year industry according to these mainstream projections for the future, and that would be how you'd sell it to people. And there are a few promising or fledgling projects here and there. But we've seen before with CCS for the power industry how dangerous and difficult the road can be. So ultimately, I'm sort of as nonplussed as ever. I don't want to dismiss DAC because of its large potential and simplifying advantages compared to other negative emissions technologies. But ultimately, that high cost makes the barrier for the already unlikely large-scale adoption of negative emissions that much higher. So while I wish everyone working on the technology success, I wouldn't be that surprised in the long run if the life support system for Spaceship Earth remains a concept in sci-fi. Concluding then, I'm going to try and briefly summarise what we've learned and discussed about negative emissions throughout the series, and conclude with some thoughts for the future. Over the last dozen or so episodes, I've talked about the idea of negative CO2 emissions at real length, although as ever when I choose a complicated topic to cover, you get the sense we've only scratched the surface of the field. But we've talked about the politics, the economics, the science, the comparative technologies. We've talked about the environmental impact and the implications for climate policy that might arise from different methods of pursuing negative emissions. We've described various different methods by which you might do this, either by enhancing natural sinks of carbon, like through rewilding nature, planting trees, or encouraging soil carbon sequestration, or engineering new ones with carbon capture and storage. Some people might suggest that doing this series is, in itself, an indulgence. After all, one point you've heard me repeat till I'm blue in the face is just how difficult it is to remove greenhouse gases from the atmosphere at a scale that really matters for the climate. We know that this is not a magical techno-fix that will allow us to build a few factories here or there, or plant a couple of trees to allay our carbon sins. There are real concerns that we might end up just selling indulgences that let us think that we're getting away with that sin when we're actually not. But for this to make a real impact, the activity to remove CO2 has to be comparable to the activities that are currently dumping it into the atmosphere. This is not even physics, this is accountancy. But when you actually think about the implications of that, it makes for eye-watering engineering, political, environmental and economic challenges. For that reason, again and again, we have emphasised the difficulty of leaning too much on negative emissions. We've emphasised again and again, and the fact that it will likely in general be much easier, faster, cheaper, to do everything we can in the near term to reduce emissions, replace fossil fuels with clean alternatives, curb unnecessary consumption and environmental destruction and degradation, and so on. We've talked about how the most reasonable use for negative emissions is really to mop up that last few percentage of our emissions that are hard to avoid in these conventional ways. And therefore, we think of David Mackay's point that this is the last thing we should be thinking about. And yet it is also something we should be thinking about. As such then, we might expect these negative emissions to be deployed in a radically different society. One with a system for the production and harnessing of energy that looks very different to today's. There is a criticism of climate and energy types, and I think often a fair one, that we can disproportionately devote ourselves to arguing about the best way of dealing with this 5% or 10% of difficult to mitigate, when the vast majority of the action that needs to take place is a lot less sexy, doesn't focus on new technologies, it's happening elsewhere, and it requires just a big scale-up of technologies that already exist and work today. And after all, today negative emissions per se account for a tiny, tiny fraction of all anthropogenic emissions for CO2. Most of what we're doing is dumping billions of tonnes into the atmosphere every year. Talking about bailing out the bath before we've switched off that tap can seem like putting the cart before the horse, and with good reason. Yet there is an obvious reason for me to talk about these technologies on this show, and I think that really comes from our fascination with them. The questions posed by the idea of them. These things have their own impacts. We've already seen, and I've described in great detail, how many of the climate plans that influential models and modelers spit out that are appealed to or leaned on for understanding by politicians and policymakers, that exist perniciously in the backs of the minds of the people who think about climate change and decarbonisation on these grand scales. We think about how all of these things have increasingly come to depend on these saviour technologies. In this context, there is a lot of mythology, confusion, misconceptions at play. We have to dispel notions that people might have initially on hearing of these ideas for the first time, like maybe the idea that natural solutions are always necessarily vastly superior to engineered ones, and don't have their own set of different consequences to think about. Or the idea that we can continue on with business as usual fossil fuel consumption providing we build enough direct air capture machines or plant enough trees, or use some unbelievable ingenuity to invent a magic bullet solution to climate change that will resolve a problem of gigatons of gases emitted by thousands of different processes, and still deeply entwined with the vast majority of the ways that we humans harness energy in one fell swoop. We have to interrogate difficult questions of moral hazards, justice, ethics, and the feasibility of the different futures that we can consider. We have to consider which policies and what political implications arise from a world where negative emissions play a role. We have to cut through the greenwash of fossil fuel companies who pretend a little seed capital here and there to a BECCS or CCS project is going to be sufficient to offset what they're doing. We need to seriously assess the potential of technologies like utilising CO2, when most of the analysis on this question is done by people with vested interests in it. We need to critically assess the carbon storage potential of restoring ecosystems, even when our environmental instincts tell us it might be the right thing to do for many other reasons. And nor can we, the majority of my listeners now sitting in Western industrialised nations, blithely lay claim to vast swaths of territory in the tropics to devote to producing biofuels, to burn and bury, to make up for our continued carbon emissions. We need to look back through the history of technological developments, and then try to project this into the future. We need to understand why some technologies take off and others don't, and whether there's anything we can do about that. We're ultimately trying to determine which visions of the future are viable, and whether and how we can get there. And to paraphrase Niels Bohr, the great quantum physicist, making predictions is hard, especially when they're about the future. We have talked about the pernicious effect of ratcheting up our dependence on negative emissions as an alternative to near-term action. But we've also discussed some of the undeniable advantages that a developed industry or means of producing negative emissions could have. For equity and justice purposes, this gives us the real option for people who have historically damaged the climate to pay genuine climate reparations by actually cancelling out their historical emissions. This same schema could be perhaps applied in part to wealthy countries. Sectors which might otherwise be forced to go out of business can continue operating, which ultimately might prove more practical and achievable than alternatives where they simply cease to exist. If we overshoot our temperature targets and find that climate tipping points like the melting of ice sheets are being triggered, then large-scale negative emissions, or solar radiation management, geoengineering, may be options we need to understand in more detail as potential ways to stabilise the climate. And if we ever did need to resort to solar radiation management, or if we ever did resort to it, then we would need negative emissions to extricate ourselves from that. And this argument very much is still ongoing. Even as I write this, yet another Nature paper has been published pointing out that the assumptions which go into models are crucial in determining how much negative emissions we need to meet our climate targets, and that there is a trade-off between near-term action and depending on these technologies in the future. We told you this episodes ago, but it's not a talking point. People have actually done the maths on this and shown how our assumptions about how these technologies will develop really shape what we're telling ourselves that we need to do in the next few years. There is a good set of arguments that says that David Mackay was right when he said that negative emissions really are the last thing we should be thinking about. But he may also be right in the sense that we do need to think about them. And while they exert this grip on the imagination of policymakers, technologists, modellers and scientists, the debate is getting louder. Now, you may have listened to the series and come away with the conclusion that some level of negative emissions is necessary for decarbonisation. Or you may think that the whole thing is a total folly. Or you might be more optimistic than that and think that they really can play a major role with the right incentives. Please get in touch with your opinions if you have them via the contact form on our website, and if there's enough we might even have a response episode to what you've heard. I'd be interested in that. Despite having studied this for a long time though, and I admit maybe becoming increasingly cynical about the potential for these types of solutions to come along and save us, I'm still not 100% convinced of the future that we will all end up in. We need to have that debate in an informed way so that we can take the appropriate actions and decide on them together. I hope that by laying out some of the issues with negative emissions in general, and comparing particular technologies, whether the issues associated are political, technical, and economic, scientific, or environmental, in this series of episodes that I have helped in a small way to inform that debate. Thank you for listening to this episode and this series from Physical Attraction. When we come back, we'll probably be talking about something completely different, but thank you for indulging me yet again for another mega series covering a topic that I'm fascinated with. You can get in touch with us in many different ways with any comments, questions, or concerns that you have about the show. Any feedback you have is greatly appreciated. Please go to physicspodcast.com. You'll find the contact form there. You can get in touch with us, and I try to respond to as many emails as I can. You'll also find us on the web. We're on Twitter at PhysicsPod, and you can join the Science Podcast Facebook group. We have a Reddit page as well, which is not very well used at the moment, but you can get involved with that if you should wish. There are many ways that you can support the show, which you will also find on our website at physicspodcast.com. You can make a one-off donation. You can subscribe on the Patreon. Many of you listening to this early will have subscribed on the Patreon, and thank you for your continued support of the show. I really appreciate it. If you want to join those people, you'll get early episodes, you'll get improvised episodes, you'll get bonus episodes that aren't available anywhere else, and so I strongly recommend that. Of course, one of the greatest things you can do to support us is to tell other people who might be interested in us, people who've maybe mentioned some sort of negative emissions idea to you. You can say, guys, have I got the podcast series for you? And let them know. And we rely a lot on word of mouth for new listeners to be accrued to the show, and suggestions for topics as well. So please do that if you want to help support the show. That's enough from me. Until next time then, please do take care.